So please help me welcome our speaker this evening, Dr. Jeff Bennett.
Thank you. Thank you all for coming out tonight on a Friday night. I appreciate it. I know it's Halloween, so a lot of competition for your attention tonight. Those of you who've seen me before know that I do a fair amount of speaking about science, but this is the first time I've done public talks on this particular topic, so I especially want to thank you for being here as my guinea pigs tonight. And so we'll see. My goal tonight partially is to see how this works, because I hope to do this talk in other places, but you can all let me know afterwards what you think, if it's worth taking it elsewhere, and what suggestions you have for improving it. I would appreciate that feedback. Now, you may wonder what I, as an astronomer, am doing here talking about global warming. And part of the answer is that, as we'll see, global warming actually comes from a lot of astronomical understanding of the planets. But in my particular case, we can trace it back to Einstein. This year is the 100th anniversary of Einstein's general theory of relativity. And because relativity is a topic that so many people have heard about, but very few people know much about, I decided that I would go out on a national relativity tour to talk to people about Einstein's theory. And as you can see from the list, it went better than I had expected. I ended up in about 25 different cities, talking to more than 10,000 people in total. And I've had such a good time doing it that I was kind of sad about 2015, this 100th anniversary, coming to an end, which meant I didn't really make sense to keep talking about that topic. And therefore I thought, well, maybe I can do something else for next year. And so I thought, well, it should be something else that I've taught about and written about for a long time. It should be something else that a lot of people have heard about, but very few people really understand. And you can see that's why I picked global warming. Because as you know, almost everyone has an opinion about global warming, but when you probe more deeply, you find that very few people can back those opinions with actual evidence. Some people even state their opinions, but then at the same time will say, I'm not a scientist, when you ask them why they believe in those opinions. And so that's how tonight's talk got its name. And I have two major goals for you tonight. First, I want to convince you that you don't need to be a scientist to understand this issue. The basic science is simple enough for anyone to understand, even if the overall Earth's climate system is indeed very complex. Second, I want to convince you that this is not a partisan issue, despite what you may have heard in the media, and that the solutions are actually ones that people of all political persuasions can agree upon. And to help emphasize that point, I want to start with a quote from Ronald Reagan. Preservation of our environment is not a liberal or conservative challenge, it's common sense. Now, because I'm an astronomer, I want to start from an astronomical point of view, because as I mentioned before, a lot of our understanding of global warming starts from astronomy. Here we see the Earth and Venus, and they're shown to scale. And you'll notice that both of them are about the same size. They also overall have about the same bulk composition, which means we might expect them to be very similar in most all ways. And actually in the large scale they are, but in terms of their surface temperatures, there is a major difference. In addition to Venus being extremely hot like that, the surface pressure is so high that it's equivalent to being about 1 kilometer beneath the surface of the oceans on Earth. It has clouds of sulfuric acid, and therefore sulfuric acid rain in the atmosphere, so that overall, in contrast to Earth, which we know is a very nice place to live, Venus is probably as close to the traditional view of hell as you can get. So, incidentally, if anyone ever tells you that they think you should go to Venus, they are probably not favorably comparing you to Matt Damon in The Martian. So you might wonder, given the overall similarities of the two planets, why are their surfaces so different? Well, most of you probably know that Venus is closer to the sun than Earth, and it might be tempting to assume that that's the reason that Venus is so hot. But it turns out that doesn't quite work. Here we see the Voyage scale model solar system on the National Mall, but again, it's the same scale as the one out front here at Fisk. There's the sun, Mercury's there, Venus, and Earth. And what you can notice if you think about the sun being very hot and being at these different distances, well, sure, Venus is closer to the sun than Earth, but not by that much. It's not enough to explain that very high temperature. In fact, if that difference in distance was the only difference between the Earth and Venus, Venus would only be about 60 degrees Fahrenheit warmer than Earth, not more than 800 degrees warmer than Earth. In addition, it turns out that Venus is covered by bright clouds, as you can see there, and those clouds actually reflect most of the sunlight coming at Venus. And the odd result is that even though Venus is closer to the sun than Earth, because the clouds reflect so much light away, less sunlight hits the ground on Venus than on Earth. And that would lead us to expect Venus to be colder. And yet again, we see it's more than 800 degrees Fahrenheit hotter than Earth. Why? We know the answer today. And the answer is what we call the greenhouse effect. And this diagram shows you how that effect works. We get our energy from the sun. So sunlight comes into the Earth's atmosphere, represented in yellow here. Some of that sunlight is absorbed by the ground, some of it is reflected by the ground or by clouds. The sunlight that's absorbed at the ground heats the ground up. That is the source of our heat on Earth. The ground has to return that energy back up to space, otherwise it would keep heating and heating and heating very quickly. And the way the ground returns that energy back to space is by emitting what we call infrared light. It's a form of light that our eyes cannot see, but you can see it with infrared cameras. There's one in the lobby that you can check out on your way out. And these red arrows represent the photons of infrared light. And what you'll notice is that instead of going straight back out into space, these infrared pieces of light, they bounce around. And the reason they bounce around is because they hit these blue dots in this picture, which represent what we call molecules of greenhouse gases. Greenhouse gases include carbon dioxide, water vapor, and methane. And what makes them greenhouse gases is that they're very good at absorbing infrared light. So when the infrared light hits one of these greenhouse molecules, it gets absorbed and then re-emitted in some random direction. And the net result is that because the infrared light bounces around among these greenhouse gas molecules, we end up having more heat and more energy trapped in Earth's lower atmosphere than would be the case without the greenhouse effect. And you can see the more greenhouse gases you have, the more it's going to bounce around, and therefore the warmer the lower atmosphere will be. A good analogy to understand this is a blanket. When you put a blanket around you, as long as it's not an electric blanket, the blanket itself doesn't give you any heat. All it does is help you retain your own body heat by slowing the escape of your body heat into the outside air. The greenhouse effect is the same idea. It slows the escape of Earth's own heat and therefore makes Earth warmer than it would be otherwise. Now, I think if you were following that, you'll agree that that's a good story about why Venus is so hot, why the Earth is so hot. But in science, it's never enough just to have a good story. You have to have actual evidence to be sure that you really understand something. And in this case, it turns out we have two very strong lines of evidence that prove that the greenhouse effect really does work exactly the way I just showed you. The first is that we can actually measure the effect in the laboratory. Scientists have been measuring the heat-trapping effects of greenhouse gases for a long time. In fact, the first measurements were made way back in 1859 by John Tyndall, a British scientist. And this illustration shows you the apparatus he used. Don't worry about the details. Basically, you just put a gas in a tube like carbon dioxide, shine some infrared light on it, and see how much of that light is emitted, how much is absorbed, and how much passes through. And these measurements show us exactly how much heat you expect to get from carbon dioxide, from water vapor, and others in the Earth's atmosphere. The second line of evidence comes from the fact that the greenhouse effect is necessary to explain the actual temperatures of all the planets, including Earth. And you can understand it by thinking of it like this. Imagine that there was no greenhouse effect, so that the sunlight came in and just was reflected back out and absorbed and radiated away as infrared light that went straight out into space. In that case, Earth's temperature, or the temperature of any planet, would depend on only two things. First, it would depend on how far it is from the sun, because that determines how much sunlight is coming in. And second, it would depend on how bright the planet is, how much of that sunlight it reflects, because that determines how much is left over to be absorbed and heat the planet. You can actually write a very, very simple formula to calculate the temperature that a planet would have if there was no greenhouse effect. You don't need to worry about that formula, but just to prove to you that it's pretty simple, I'll show you I even put it in one of my children's books. It's right there. And the result is the important part. This shows it for Earth, and what you'll notice is the formula shows you that without that naturally occurring greenhouse effect that we have on Earth, the temperature, the global average temperature for our whole planet would be well below freezing. In other words, our whole planet would be frozen over and too cold for life. In reality, Earth's average temperature is quite pleasant, 15 degrees Celsius, almost 60 degrees Fahrenheit. And the only way you can account for that difference is by using the greenhouse effect. And from what we know about it in the laboratory, when you do the calculations, you find it perfectly explains Earth's actual temperature. The same is true for all the other planets as well, including Venus. And that brings us back to our tale of two planets. We now can understand why they're so different. On Earth, we have enough carbon dioxide in our atmosphere to make our planet livable instead of being frozen over, which means that the naturally occurring greenhouse effect is a very good thing for life. But Venus has about 200,000 times as much carbon dioxide in its atmosphere as Earth. That creates an extreme greenhouse effect, and that's what explains Venus's extremely high surface temperature. In other words, while the greenhouse effect is a very good thing for life on Earth, you can think of Venus as being absolute proof that it's too much. It's possible to have too much of a good thing. Between the laboratory measurements and planetary temperatures, there's no doubt that the greenhouse effect is real and that more greenhouse gas makes the effect stronger. And this is the beginning of where our concerns today about global warming come in. Because what we've discovered is that in addition to understanding the greenhouse effect, we now know that we are increasing the concentration of greenhouse gases, particularly carbon dioxide, in our atmosphere. This graph shows you how we know that. This shows you direct measurements of the carbon dioxide concentration that were begun in 1958. On this scale here are the measurements we use for carbon dioxide, which is called parts per million, which basically means how many molecules of carbon dioxide there are for each 1 million molecules of air. And what you'll notice is we have a clear upward trend that has been occurring since this began to be measured. Some people wonder, how do we know that this increase is due to us rather than being a natural increase? And we have 3 lines of evidence that tell us that this increase is due to human emissions of carbon dioxide. The first is that it actually tracks virtually perfectly with our emissions. This graph shows you the amount of carbon dioxide that we're releasing into the atmosphere over time, mostly coming from the burning of fossil fuels, coal, oil, and natural gas. And you'll notice that its upward trend is basically exactly the same as the upward trend I showed you for the carbon dioxide. In fact, it turns out that not all of this carbon dioxide is staying in the atmosphere. About half of it stays in the atmosphere, and the other half dissolves in the oceans, which is an important point that I want you to remember because I will come back to it later. The second way we know that it's our carbon dioxide is because there's really no other possibility. When you look to see other sources of carbon dioxide being added to the atmosphere, the only other significant one is volcanoes. This shows you the estimates of the minimum and maximum that's emitted by volcanoes each year, and in proportion, that's human emissions of carbon dioxide, and you can see there's no comparison. Volcanoes emit less than 1% as much carbon dioxide into the atmosphere each year as we do. And if those two things are still not enough to convince you that the carbon dioxide is coming from us, there's actually a smoking gun that shows without doubt that it is coming from the burning of fossil fuels. And that comes from the fact, as some of you may know, carbon comes in more than one different form. We call them isotopes of carbon, carbon 12, 13, and 14. And the ratio of different isotopes of carbon is different in fossilized carbon, because that's carbon that was once alive in living organisms. It's different in fossilized carbon than it is in carbon from other sources. And that means that when we burn fossil fuels, the carbon dioxide that ends up in the atmosphere has a different isotopic signature than the carbon dioxide that comes from other sources. You don't need to worry about the details of this graph, but in case you're interested, this is showing you the change in the isotopic ratio of two forms of carbon here, and you'll notice that's going down at exactly the same time that the black shows you the amount of carbon dioxide in the atmosphere going up. This shows you there's no other possibility other than that the carbon dioxide is coming from the burning of fossil fuels. Now, so far, I've only shown you the carbon dioxide since 1958, because that's as far back as the direct measurements go. So you might wonder, well, what about further back? How different is what we're doing today from what happened further in the past? And even though we didn't have direct measurements before 1958, we are still able to figure out how much carbon dioxide was in the atmosphere for much longer times in the past. The longest and most reliable records come from studying air bubbles that are trapped in ice that has remained frozen for long periods of time in Greenland and Antarctica. The basic idea is pretty simple. Scientists drill down into the ice and they bring up what we call an ice core. And this ice core, it's got layer after layer that represents the compressed snow that fell year after year after year. So you can read that ice core just like reading tree rings, and you can find air bubbles trapped in the different layers in that ice core, measure their carbon dioxide concentration, and thereby know how much carbon dioxide was in the atmosphere at different times in the past. Amazingly, the longest ice core ever drilled is 2 miles long. It was drilled 2 miles down into the Antarctic ice, and it represents snows that fell over the last 800,000 years on Earth. And therefore, we actually have a record of the carbon dioxide concentration going back 800,000 years. And it's shown here in this graph. Again, we see the carbon dioxide concentration in parts per million over here. We have the present over here at 0, and going back, these are in hundreds of thousands of years, so we go all the way back to 800,000 years ago. And what you'll notice is that the carbon dioxide concentration naturally varies quite a bit. But throughout that 800,000 year period, it has always remained between about 180 parts per million and 280 parts per million until the last couple of centuries, where it's gone all the way up to 400 parts per million today. In other words, today's concentration of 400 parts per million is about 40% higher than it's been at any other time in the past 800,000 years. In fact, if you extrapolate this trend into the future, you find that if we continue to emit carbon dioxide as we are today, we will reach double the pre-industrial concentration of 280 parts per million, double that is 560 parts per million, in only about 50 or 60 years from now. We'll be at triple that concentration, or 840 parts per million, by the middle of the next century. And that right there is why I've told you that I think you don't actually need to be a scientist to understand this issue. Because if you think about what we've talked about so far, I think you can say that global warming, at least in its most basic science, is as simple as 1, 2, 3. So let me go back through it. 1, I've shown you the evidence that leaves no doubt that greenhouse gases like carbon dioxide really do make planets warmer than they would be otherwise. 2, I've shown you the evidence that leaves no doubt that human activity is increasing the carbon dioxide concentration. And if you think about those two facts, they lead to an inevitable conclusion, which is our 3, which is that unless we're missing some major piece of this story, we should expect the Earth to be warming up as a result of the fact that more greenhouse gases mean more warming, and we know the greenhouse gases are increasing in our atmosphere. So I want you to think about this argument look at this very closely, because I think this simple 1, 2, 3 piece is the single most important piece of the entire discussion of global warming, and also the single most forgotten piece in the discussion of global warming. Because what you'll find is that people debate details, they debate solutions, they debate implications and predictions, but this part is very clear and very simple, and it tells us that we have something that we need to be thinking about. It doesn't tell us how bad it's going to get. We'll talk about that in a little bit and what the uncertainties are, but it does tell us that it's a real issue. And just to show you that this is not a political issue, it's simple science, I'll give you a quick audience quiz. Who was the first global leader to speak out about this issue on the international stage? Okay, I hear a few guesses out there. When I've asked other people, particularly students, this, the most common answer is people think it was Al Gore. And Al Gore actually was studying this issue probably before many other politicians were. But in 1989, he was still just a senator when the conservative British Prime Minister, Margaret Thatcher, went to the United Nations and said this: "What we are doing to the world by adding greenhouse gases to the air at an unprecedented rate is new in the experience of Earth. It is mankind and his activities which are changing the environment of our planet in damaging and dangerous ways." Again, notice that this is a conservative speaking more than 25 years ago. Now, I told you that you don't need to be a scientist to understand this issue, so some of you may know it's a little bit unfair of me to put Margaret Thatcher up there because she actually was a scientist. Her degree from Oxford was in chemistry, and she actually did some research in chemistry before she became a politician. So to prove to you that you don't have to be a scientist to understand this issue, here's a quote from the United States president at the same time, George Bush Sr., who was not a scientist, and you can see he came to exactly the same conclusions as Margaret Thatcher. So let's go back to our 1, 2, 3 science. Given how simple this idea is, you might wonder, why do we hear so much debate in the media? Some of it is ignorance, people who've never bothered to take the minimal effort needed to understand what we've just gone through in a few minutes here tonight. But there are also some real scientists who count themselves as global warming skeptics, and we have to take their arguments seriously. And therefore, before we decide how big of a problem this is, I want to spend a little bit of time looking at the arguments made by the scientific skeptics. But first, I want to point out once again that while they're going to argue on some of the details and the predictions, and we'll talk about that, no one disputes that 1, 2, 3 science. And here's a quote from one of the leading scientific skeptics, the one who's arguably the most well-known and the best credentialed, MIT professor Richard Lindzen. And you'll notice he says very clearly the debate is not about the carbon dioxide concentration increasing. It clearly is. It's not about whether the increase in carbon dioxide by itself will lead to some warming. It should. Exactly what our 1, 2, 3 argument says. The debate is only about how much warming and the connection of that warming to potential catastrophes. If we consider the debates that the scientific skeptics are, the points that they're arguing, we can broadly divide them into 4 categories. The first is that despite our 1, 2, 3 expectations, maybe Earth isn't warming up yet. Maybe, even though the basic science is very solid, maybe there's something missing in the story that prevents the Earth from warming up the way we might expect. Now, this argument was probably a valid argument a couple of decades ago when there were some uncertainties in the temperature records and the measurements. But this particular one no longer works, and you can see why. This graph shows you global average temperatures going back as far as we have reliable records to 1880, up to the present, compared to the 20th century average, and you can see there's been a clear upward trend. The global average temperature today is about 1.5 degrees Fahrenheit higher than it was a century ago. This next graph makes the case even stronger. In this graph, you see this blue curve is the same temperature data I just showed you, but plotted as what we call a 5-year running mean to smooth out some of the variations from year to year. And this green curve is the rising carbon dioxide concentration. And you'll notice they're going in tandem exactly the way our 1, 2, 3 science tells us to expect. I also want to point out here that some of you have probably heard the claim that global warming has stopped during the past 15 years. This graph only goes to 2010, but I calculated the values going all the way to the present. And what you'll notice is that the most recent 15 years are the hottest 15-year period on record. The most recent 10 years are the hottest 10-year period on record. The most recent 5 years are the hottest 5-year period on record. Last year, 2014, was the hottest single year on record. And this year, 2015, is on track to break last year's record. So while there may have been a bit of slowing in the rate of increase, particularly in here, that rate of slowing seems to have gone back up. It's speeding up again. But if anyone tries to tell you that global warming actually stopped, it's pretty clear that that is not the case. So with that skeptic's first point of debate no longer viable, let's turn to the second, which is that despite the close correlation we've seen between carbon dioxide and the rising temperature, perhaps there's still a natural explanation for the warming to date. Maybe there is something natural that explains that warming that I just showed you. The most commonly suggested natural cause is the sun. So I've got a graph for you here that shows the rising temperature since 1880 again to the present, and it shows the sun's energy output. And what you'll notice is that for a while they were kind of moving together, but over the past few decades the temperature has kept going up while the solar output has actually gone down. And that right there means there's no chance that the sun is the cause of our recent global warming. And in fact, it seems highly unlikely that any other natural cause could be responsible either. And the reason is because scientists have a way to explore those natural consequences. And the way they do it is by building what we call computer models of the climate. We can't actually do experiments on the real planet changing things, but we can do it by building models in the computer to see what happens. This graph shows you again, the same temperature data in black that I've shown you before, and the red shows you what today's global climate models predict should have been happening over this time. And what you'll notice is that the predictions, they're not perfect, but they match up to the actual measurements pretty darn well. That gives us confidence that these models are on the right track, even if they're not perfect. But now, these models, they're taking into account everything that's going on in the atmosphere, including the human contributions to global warming. If we take the human contributions out of the models and rerun the computer experiments, you get the blue curve. And what you'll notice is it worked pretty well 100 years ago, but today, it doesn't work at all if you take the human contributions out. So natural factors do not seem to explain the warming that we have underway. Sometimes people talk about the fact that we cannot expect the models to be perfectly reliable, which of course is true. There's always uncertainties in the models. But the models seem to work very well, and they tell us that we will have a deeper problem in the future. And that more than any other single thing, the fact that the models seem to be working very well so far, and they're giving us dangerous predictions for the future, explains why the vast majority of scientists who've studied this issue, more than 97%, believe that this is a serious problem that we need to deal with. And it's only a very small minority of scientists who think there may still be something big enough missing in our models to alleviate the concerns of the temperature continuing to rise. And that brings us to the third debate point, which is that even accepting that global warming is real and human-caused, it's not something that we should be overly worried about. And the most common argument given here is that the climate changes naturally, and it does. This graph shows you the global temperature record reconstructed from various different sources, tree rings, coral reefs, and other things, a number of different methods, for the past 1,000 years, 1000 AD and the present here. And each of these curves represents the temperature reconstruction in a different color from a different method. And you'll notice, as you might expect, that they don't agree with each other perfectly, these different methods, because there's always uncertainties when you try to put together what happened in the past from fossilized data. Nevertheless, what they all show is that the climate has indeed varied naturally long before the Industrial Revolution began. For example, this part in here where it was relatively warm is the famous medieval warm period when the Vikings were able to colonize the coast of Greenland. But what you'll also notice is that even though there's been plenty of natural variation in the climate, what's happening today is going way beyond anything that happened naturally in the past 1,000 years. We can go back even further using the ice core data that I showed you before. Here's the same graph that I showed you before of the carbon dioxide concentration, but this time I've added a graph that shows you what we've learned about the temperature from those same air bubbles during that whole period. And again, just like the carbon dioxide concentration has varied naturally, you'll see the temperature has varied naturally. The cool periods are ice ages, and the warm periods come in between. Incidentally, you might wonder, why does the temperature vary so much for natural reasons? And the answer is that it's traced to small changes in Earth's orbit and axis tilt. Some of you may have heard of these being referred to as the Milankovitch cycles, which you can read about more elsewhere. But for tonight, what I want you to do is just focus on two facts about this natural change. The first is notice that these natural changes from the coldest to the warmest are quite substantial. Easily 8 to 10 degrees Celsius, which is 14 to 18 degrees Fahrenheit, which is actually very interesting because remember, some people are concerned that the models might not be that reliable about what they're predicting for the future. But none of the models predict temperature changes for the next century at least as large as what has occurred naturally in the past. So if you don't want to believe the models, your alternative is to believe the actual data, which would make the problem look even worse. Second, notice that while the temperatures that we've recorded today are not out of line with some of the others in the past, the carbon dioxide level is out of line with anything that's happened in the past 800,000 years. And again, that's why we have great concerns about what will happen to the temperature as we go into the future. Because what we are doing today, as Margaret Thatcher said, really is new in the experience of Earth. If you go back even farther, though, we find times in Earth's history when it was much warmer even than anything in this past 800,000 years, and when the carbon dioxide concentration was much higher, and a few skeptics have pointed out that life did just fine under those conditions, which is true. This painting, for example, shows you what Antarctica may have looked like about 100 million years ago, when the Earth was so warm that there were no polar ice caps, and the carbon dioxide concentration was above 1,000 parts per million. But personally, I don't find this very comforting. Life did fine because it was adapted to that climate. Today's life is adapted to today's climate, and it's not likely to do so well if the climate becomes warmer very quickly, as it appears to be doing. Moreover, remember that while 1,000 parts per million may sound very high because it's more than double our current 400 parts per million, at our current rate, we would still reach this in less than about 200 years. Clearly, we cannot let things keep going like that. So now we'll turn to the fourth common point of debate, which accepts that global warming is a real problem, but claims that it's really not cost-effective to do anything about it. In other words, it's a problem, but it's not that bad of a problem, and therefore it's not worth spending a lot of money on. And to consider this claim, we need to consider the costs of not acting. And to do that, we need to understand the consequences that we expect from global warming. So I'll now try to explain the basic science behind the major expected consequences. The first is that global warming does not affect the entire planet the same way. Global warming is referring to the average rise in the temperature on Earth. Some places are going to warm more or less than average. And I have a little video here for you that shows regional temperature changes that have occurred since 1880. And so blue is cooler, red is warmer. There's the temperature scale over there. You can see the years going by. And you'll notice that, 100 years ago, got warmer, got cooler, got warmer, got cooler. But as we start to move towards recent decades, watch what happens. This is the actual temperature data. You'll notice the polar regions have already warmed enormously, which you can see in the melting of ice and other things out there. And what I want you to do is play that video in your head again and think about, if you extrapolate that 50 to 100 years from now into the future, what it would look like. Also remember that temperature is not the only thing that's changing. Rain and snowfall patterns also change, and many scientists suspect that such changes are behind at least some recent floods, droughts, and increases in wildfires. Indeed, these changes have also been implicated in such things as the spread of the pine beetles that are killing our Rocky Mountain forests and the increased range of many agricultural and disease-causing pests. The second major consequence we expect from global warming is more extreme weather events. And it's easy to understand why. Remember what I showed you in the beginning. What the greenhouse effect is really doing is trapping energy in Earth's lower atmosphere. That energy, part of it comes in the form of heat, but we also know that energy is what drives the weather. And therefore, more energy means we should expect hurricanes, thunderstorms, tornadoes, and other extreme weather events to become either more numerous, more severe, or both. It's worth noting that this includes severe winter weather, leading to the ironic result that global warming is very likely responsible for some of the extreme winter blizzards that have occurred in recent years. Of course, we cannot tie any particular storm to global warming. The analogy that climate scientists like to use is to loaded dice. Just as rolling loaded dice makes certain outcomes more likely than they would be otherwise, global warming makes extreme weather events more likely than they would be otherwise. This year offers a good example. Last week's Hurricane Patricia, this is a picture of it taken from the International Space Station, was one of the strongest hurricanes ever recorded, and it's coming in the most active hurricane season on record. We cannot say that this particular storm or this season were caused by global warming. What we can say is that global warming makes storms like this and seasons like this more likely, and that we can therefore expect more years like this in the future. A third consequence is that the added heat causes ice to melt. Let's start with sea ice like that up in the Arctic Ocean. This map shows you what's happened with the summer ice coverage. The red shows you the summer ice extent in 1980. The pink is for 1998. And the white is for 2012. And you can see there's been a dramatic decline in the amount of summer sea ice in the Arctic. This has many detrimental effects. Most famously, it hurts polar bears that depend on the ice in order to hunt seals, but it also affects weather patterns, and it's been implicated in jet stream changes and the so-called polar vortex that has caused some strange weather in the US in recent years. Even worse, this melting of ice actually amplifies global warming. And again, the reason is easy to understand. Ice reflects a lot of sunlight. Water does not. So when ice melts into water, more sunlight is absorbed, and more absorbed sunlight means warmer temperatures. A fourth consequence is a rise in sea level. This rise actually comes from two distinct processes. First, although we don't usually notice it, water actually expands slightly as it gets warmer. This thermal expansion effect has already caused sea level to rise about 20 centimeters over the past century, and it's expected to cause a rise of another 30 centimeters, about a foot, before the end of this century. While that may not sound like much, it will cause flooding in some low-lying regions and cause storm surges like those that occurred with Hurricane Sandy to be much larger. The second contribution to rising sea level comes from the melting of landlocked ice, particularly in Greenland and Antarctica. Scientists cannot yet predict ice melting very well, but most experts expect the melting of ice to increase sea level by at least 1 meter and possibly a few meters before the end of this century. This will have severe consequences along coastlines. For example, the red on this map shows you regions of the southeast that will be flooded by a 1 meter rise in sea level, which most people think is inevitable at this point. And the yellow shows you regions that would be flooded by a 6 meter rise. I'm being very serious when I tell you that I would not invest in beachfront property today. At least not if you plan to hold on to it for the long term. And if you want to really understand that long-term threat, consider this fact. If the ice caps completely melted, sea level would rise by more than 200 feet. Although this worst-case scenario would probably require many centuries to unfold, some scientists think we've already passed the point of no return on it, which raises the dismaying possibility that our descendants may need deep-sea diving equipment to visit the remains of our coastal communities. The last major consequence that I want to discuss for global warming is what we call ocean acidification. Remember what I told you before, about half the carbon dioxide we're putting into the atmosphere is actually being dissolved in the oceans. And what it does in the oceans is it makes the water become more acidic. This ocean acidification has been implicated in the killing of many coral reefs, and it may be contributing to the decline of fisheries upon which millions of people depend for livelihood and food. It's also an important thing to think about if you've heard of some of the so-called geoengineering schemes to try to counteract the effects of global warming, because most of those schemes talk about things that might cool Earth by, for example, putting particles up in the atmosphere to reflect sunlight, or even mirrors out in space to reflect sunlight. And while such things could, in principle, offset the warming by letting less sunlight through, they don't do anything to change the carbon dioxide concentration. And that means they wouldn't do anything to help with the problem of ocean acidification, which is a very serious problem. Now, keep in mind that how bad all these consequences become is not yet known, because it depends on how much carbon dioxide we continue to add to the atmosphere. So again, what scientists do is they use models to predict under different scenarios what will happen to the temperature, the global average temperature in the future. This graph shows you 3 different potential scenarios for how we might change the carbon dioxide emissions that we're putting out in the future and what each of them would mean. And I'm going to skip over the top 2, which you can see are very bad, and focus on this bottom curve, because to me this is the one that worries me the most. You'll notice this shows you how much carbon dioxide we're adding each year into the atmosphere. So this is what we've been doing already, the increase. And this bottom curve says, what if we drop it a lot? What if we manage to get our carbon dioxide emissions down to half of what they are today by 2050 and down to virtually nothing by 2100? Even in that case, we still expect a warming of 2 degrees Celsius, or about 4 degrees Fahrenheit, by the end of this century. I think the lesson is clear. What we're seeing here is that even on what most people consider an excellent scenario of dropping our carbon emissions a lot, we still have a very serious problem to deal with. And that's why we go back to that forced skeptic argument about cost effectiveness. If you believe that these problems are very serious and need to be dealt with, the only way to deal with them is to drop our carbon dioxide emissions even more than what's shown here. In fact, to really deal with it, we would need to essentially stop emitting carbon dioxide, which means stopping our use of fossil fuels. That's not easy. It requires a big change to the global economy since we have a fossil fuel-based economy. And that might make you sympathetic to the argument that it's not cost-effective or that it would be too expensive or too difficult. But I disagree, and in fact, I believe that solving this problem would actually save us money and boost our economy. So I want to explain briefly. The first thing you need to know is that we actually could, in principle, easily solve the problem right now. We could switch away from fossil fuels by replacing them with technologies that we already have, in particular nuclear and renewables, solar and wind. And you probably know that some of the prices of these are coming down fast enough that some of this is already going on. Beyond these technologies, we have many other technologies that are on the horizon, including biofuels, solar power from space, and nuclear fusion. And just to give you an example of how promising some of these technologies are, I want to talk very briefly about fusion, because fusion is the power source of the sun. And the problem we have, the reason we don't have commercial nuclear fusion today, is basically because we haven't figured out yet how to do what the sun does. But imagine that we did. Imagine that we borrowed your kitchen sink, turned on the faucet, let the water run through it. Well, water is H2O, so we could take the hydrogen out of that water and put it into our fusion reactor. So imagine that we did that and just took the energy that we got from the water flowing through your kitchen sink, and that's all. How much energy could we generate from it? I've given you some multiple choice options here, so you can think about which one you would pick. I won't poll you right now, but the correct answer is E. With your kitchen faucet, we could power the entire United States. The fusion reactor hooked up to your faucet, taking the hydrogen from your water, would provide enough energy to replace all the coal, all the oil, all the natural gas, even all the traditional nuclear and solar and wind that we use in the United States today. That's an incredible promise. You might wonder, how hard are we working on this issue? Well, people certainly are working on this and have been for a long time, but as a nation, we spend more on pizza every week than we spend on fusion every year. Anyway, given that whether it's with these new technologies or our existing technologies, nuclear and renewables, given that we know how to solve this problem and we have ways to solve this problem, why aren't we doing it? And a lot of people have different opinions about this, and I'm going to move away now from what I hope has been just solid science up to this point to giving you my opinion about why I think we've had trouble. And I think the reason is because even though the prices have been coming down, it's still cheaper to use fossil fuels than it is to use these alternative technologies. And the reason it's still cheaper is, well, I'll give you a surprising answer. The reason it's still cheaper is because we're actually practicing socialism when it comes to energy. Let me explain. We have a lot of costs that are associated with fossil fuels that we don't pay as users, but instead we socialize across society. For example, the National Institutes of Health say we spend at least $120 billion per year on pollution-related health costs. Those costs are not paid when you buy the fuels. Instead, they're paid by taxpayers and in insurance premiums spread out across all of us. The Defense Department says that at least $100 billion per year of our defense budget is going to protecting our energy supplies in the Middle East. And if you just take those two costs alone, which have been socialized instead of charged to users, if you spread those over gasoline, those two alone represent a subsidy of more than $1 per gallon on every gallon of gasoline that we buy in the United States. That's only the beginning. We also offer fossil fuel companies billions in direct subsidies for exploration and production and tax write-offs that cost the rest of us real money. We also don't charge them much of anything for retrieving a limited resource from the ground. There's also the fact that oil revenues have been fueling terrorism and totalitarianism around the world, which cost us not only economically, but also in human lives. There's the environmental damage from spills and strip mines. And there's much more. Indeed, if you calculate all the socialized costs of fossil fuels, you would find that they probably add up to at least the equivalent of several dollars per gallon. And just to show you that I'm not just making this up here, the International Monetary Fund did a study this year and calculated that global subsidies for fossil fuels, before including any of the economic costs of global warming, are currently $4 trillion per year. Clearly, at least to me, if we stopped subsidizing that and instead charged the actual cost of fossil fuels, we would very quickly find that all those energy sources that I've talked about before would become not only cost competitive, but cheaper. And so now I'll tell you what my personal solution to all of these problems is, which is simply stop the socialization of the costs and use the power of the free market by charging those costs back to users with a carbon tax. And I should point out that this is not my idea. In fact, if you look to economists, you'll find that both liberal and conservative economists all agree on this point, that a carbon tax is the correct and best way to let the market solve this problem for us. The only difference between the conservative and liberal economists is in how they would use the tax revenue that would come in. The conservative economists generally want it to be revenue neutral, so that we offset the carbon taxes by reducing other tax rates or by returning the money to taxpayers directly in the form of dividends. The more liberal economists tend to say, well, we can use this to fund other programs. That's a debate that we can easily have. The debate that we should not be having is over the 1, 2, 3 science and understanding that this is a real and a serious issue. It's also worth noting that there's no downside, as far as I can see, to this. If we did this, I believe the free market would very quickly come up with technologies that would replace fossil fuels, not only making it cleaner, but also cheaper. And if we make it cheaper, that means not only would we adopt these technologies in the United States, but people around the world would buy them from us. So we would solve the global problems at the same time that we would be promoting the American economy. And once more, to show you that this is an issue that I think goes well beyond politics, I want to show you a quote from the 4 EPA administrators who served the last 4 Republican presidents. "We served Republican presidents, but we have a message that transcends political affiliation. The United States must move now on substantive steps to curb climate change, at home and internationally. There is no longer any credible scientific debate about the basic facts. The costs of inaction are undeniable, and the window of time remaining to act is growing smaller." I also want to have you think about it in a slightly more personal way. There's an average of about 25 years between each generation, kids to parents to grandparents. And that means that on average, every one of you out here tonight is about 50 years older than your grandchildren are or will be. In other words, in 50 years, if you have grandchildren, on average, they'll be your current age. So I want you to imagine that you write a letter to your grandchildren 50 years from now. You write it like this: "Dear grandchildren, as I write this in 2015, many people are arguing about whether global warming is a real problem, and if so, how serious it will be for you when you are my age. I have examined the evidence, and I have decided to," and then you can fill in what your decision is about what you want to do about it. Hope your world is a good one. Then take that letter, put it in a time capsule, and leave it for your grandchildren to open 50 years from now, and ask yourselves, when they open it, how will they feel about the decision that you made? And I'm going to close with a couple of more quotes while you think about that. The first was spoken actually just last week by Congressman Paul Ryan, the new Speaker of the House. He was speaking in the context of his decision to run for that office, but I think it's very appropriate to our time capsule letter. He said, "My greatest worry is the consequence of not stepping up, of someday having my own kids ask me, when the stakes were so high, why didn't you do all you could do? And why didn't you stand and fight for my future?" And to close, I'm going to give you one more quote from the icon of modern conservatism, Ronald Reagan. What is a conservative, after all, but one who conserves, one who is committed to protecting and holding close the things by which we live? This is our patrimony. This is what we leave our children. And our great moral responsibility is to leave it to them, either as we found it or better than we found it. And that's where I'm going to stop. This slide shows you some of my books. It also has my website, and for more information about tonight's talk, you can go to the globalwarmingprimer.com website. Just very briefly, I'll point out two of my books for you. The science that I talked about tonight is actually all covered in my children's book, The Wizard Who Saved the World. And then I also have a new book, I, Humanity, that talks about how we know what we know about the universe today. And if anyone's interested, the ticket office has both of those for sale out front. And finally, I want to tell you about one other program that I'm very excited about. I had nothing to do with it, but a couple of other people decided it would be kind of cool to have astronauts read stories from space, and somehow they picked my children's books as the ones to be launched first to the International Space Station. And here you can see Japanese astronaut Koichi Wakata reading The Wizard Who Saved the World from the International Space Station. You can find the video of his reading and others at storytimefromspace.com, and I hope you'll check that out. So with that, I'll remind you that I invite your feedback on the talk, and we have time for some questions. Thank you very much.